Have you ever felt like you wanted to describe the world a little more precisely? Well, today we're going to build a toolkit, the motion toolkit. It's a new way of seeing the physics that's hiding in plain sight, and everything from a simple thrown ball to the planets themselves.
So to get started, let me ask you a kind of weird question. Just look around at the walls of the room you're in. Are they moving? I mean, your first instinct is to say, no, of course not, they're walls. But what if I told you the real answer is, well, it's a bit more complicated than that.
Because, really, it all comes down to your point of view. To you, sitting there, yeah, the walls are perfectly still. But to an astronaut floating up in space, you, your room, those walls, the whole thing is hurtling through space at thousands of kilometers an hour. And that one idea right there is the key to everything else we're going to talk about.
So, here's the game plan. We're going to start by really digging into that reference point idea. Then, we'll add two new pairs of tools to our kit, distance versus displacement and speed versus velocity. After that, we'll get into the art of changing motion, assemble our whole toolkit, and then finish up with a real mind-bender about going in circles.
Okay, first up, is anything ever really still? See, before we can even begin to describe how something is moving, we have to agree on a starting point. What are we measuring from? This is the secret of the reference point.
Picture this. You're on a bus, just staring out the window. From where you're sitting, it really looks like the world outside. The trees, the lampposts, all of it is just rushing backwards. Relative to you, those trees are definitely moving.
But now, let's just flip the script. Imagine you're standing on the sidewalk watching that same bus go by. To you, the trees are obviously standing still. It's the bus and the person inside it that are moving forward. So who's right? The crazy thing is, they both are. Motion is always relative.
And that leads us to our first official tool in the toolkit, a reference point. Sometimes called the origin, is just the spot we all agree to call still, so we can measure everything else against it. Without one, saying something is moving is basically meaningless. It's the "you are here" dot on the map of the universe.
All right, let's grab our next set of tools. These two build right on top of what we just learned. We're talking about two very different ways to measure a journey: distance and displacement. You can think of it as the scenic winding road versus the super direct straight shot.
Distance is pretty much what you'd expect. It's the total ground you covered, kind of like the number on your car's odometer. It's just a number, a magnitude. But displacement, that's different. It's the shortest possible path from your start point to your end point. And, this is the crucial part, it always includes a direction.
Let's make this real. Imagine Usha is swimming in a pool that's 90 meters long. She swims from one end to the other and then turns around and swims all the way back. So, what's her total distance? Pretty easy, right? 90 meters there, 90 meters back, that's 180 meters.
Okay, but what's her displacement? Now think about it. Where did she start? At one end of the pool. And where did she end? At the exact same spot. So the shortest path between her start and end point is nothing. It's zero. Even though she swam 180 meters, her total displacement is zero. This is the perfect example of why these two ideas are so different.
So now that we've got a handle on distance and displacement, we can unlock our next two tools, speed and velocity. This is basically the difference between asking how fast are you going and asking how fast are you going and in what direction. And the relationship here is just beautiful. It's perfectly parallel to what we just learned. Your average speed is simply the total distance you traveled, divided by the time it took. And your average velocity? It's your total displacement, divided by that same time. One uses distance, the other uses displacement. Simple as that.
Let's go back to Usha in the pool for a second. She traveled 180 meters. Let's say it took her 60 seconds. So her average speed was 180 divided by 60, which is 3 meters per second. Totally makes sense. But remember, her displacement was zero. And what's 0 divided by 60 seconds? It's still 0. So her average velocity was 0 meters per second. It's the same swim, but we get these wildly different answers, and both of them are correct.
So far, we've mostly been talking about moving at a nice, steady clip. But, the world doesn't really work that way. Things speed up, they slow down, they change direction. And to describe all of that, we need our next big tool, acceleration. It's the art of changing.
Okay, now this definition is super important because most of us think acceleration just means speeding up. But in physics, it's any change in velocity. And since velocity has both speed and direction, that means changing your direction is also a form of acceleration, even if your speed stays exactly the same.
Take a look at this data from a car. You can see that every 5 seconds, its velocity increases by the exact same amount, 2.5 meters per second. It's perfectly predictable. This steady change is what we call uniform acceleration.
Or let's think about Rahul on his bicycle. When he starts pedaling and gets faster, he has a positive acceleration. But then, when he applies the brakes to slow down, his velocity is still changing, right? So he's still accelerating, we just call it a negative acceleration, or deceleration.
Okay, we've collected all our individual tools, reference points, displacement, velocity, and acceleration. Now it's time to put them all together and build something truly powerful, something that gives us the power of prediction. And here they are. These are the equations of motion. Now, don't get scared off by the letters and symbols. Just think of these as recipes. If you know a few of the ingredients, like where something started from and how it's accelerating, these equations let you calculate exactly where it will be and how fast it'll be going at any point in the future. It's like a crystal ball for physics. For our last stop, let's take our brand new toolkit and use it on something that seems really simple, but is actually hiding a fascinating secret: moving in a circle at a constant speed.
Just watch this progression here. If you're running on a rectangular track, you have to make 4 sharp turns. On a hexagon, it's 6 smaller turns. An octagon, 8 even smaller ones. If you just keep adding more and more sides, the path gets smoother and smoother until it becomes a perfect circle, which is basically a path where you are making an infinite number of tiny, constant turns. You are always changing direction.
And this all leads to a really cool, kind of mind-bending conclusion. If acceleration is any change in velocity, and velocity includes direction, then an object moving in a perfect circle is always accelerating, even if its speedometer doesn't budge one bit. Its direction is in a state of constant, perpetual change.
So I want to leave you with this thought. Now that you have this toolkit, now that you know acceleration isn't just about mashing the gas pedal, where else can you see it? A car turning a corner, the moon orbiting the Earth, the spin cycle on your washing machine? The world is absolutely full of these invisible accelerations, and now you've got the tools to finally see them.